Yeah, it's our pleasure to have Alex Dimakis from UC Austin talking today about how generative models are the new sparsity. So please take it away, Alex.
Thank you. Thank you very much. So the title is kind of a response to a previous, to a previous talk that I will explain. The most important thing is that this is joint work with many students, including Agil, who is here. He's not here, but will be here later, hopefully. And also Yanis, who is here, Chi, who is a postdoc, and she is in the job market this year, and faculty at UT, John and Eric Price. So the joke here starts with the title of a previous Simons, but when I dig deeper, I found a more interesting story. So in 2017, we wrote this paper with Ashish and Agil, who were PhD students at the time, and Eric Price. And it's called compressed sensing using generative models. I will refer to this as CSGM throughout this long talk. So if you want to remember one acronym so you don't get lost immediately, it's CSGM. So I will explain what it is, but it's this paper. And basically we say that if you put a GAN, a generative adversarial network, as a prior, as opposed to sparsity, you get super good results in all inverse problems, like denoising, in painting, and a million other linear and nonlinear inverse problems. And then Soledad, who was a PhD student of Rachel at the time at UT, followed up and did some great work on expanding this idea. And she also wrote a blog post that had this title, "Are generative models are the new sparsity?" ? And here she just shows, for example, that if you use a generative prior, you can denoise MNIST digits much better than you could with sparsity-based techniques that, that use total variation in this example. So then in this, I don't know, was it this specific program or was it a different program? Is this program? Yeah. I don't know if it's the same program. It was like a few weeks ago or.
Part of this program.
Yeah.
Okay, so in this program then, I saw this title, and "Are generative models in sparsity" by Bruno and you know, it's the team of Florent and Lenka who are working on the statistical physics types of problems that arise in this setting that I will explain. So my talk is now coming back and saying, yes, in case you weren't worried, they actually are. So I will explain, of course, what all this means. So for the purposes of this talk, a generative model is a function that takes a k-dimensional vector that we typically refer to as z, as a latent, and produces a high-dimensional vector g of z in Rn. Rn is in the experiments I will be showing. We're working with images that are 1024 by 1024 pixels. So it's actually a million dimension, and it's actually a color image. So it's actually 3 million dimension. Okay, so we're going for 500 dimensions to a million in the experiments I will be showing. And the only two things you need to know about this function is that there's matrix multiplications and ReLUs here, ReLU activations. So it's a differentiable almost everywhere function. It's actually piecewise linear, and it's data driven. So you learn these from samples. So if, as you're initially training this, and this is for a specific way of training it, that's called the GAN, that I don't care about you knowing how GANs are trained, but you start getting things like this in the first iterations, and then after a while, you start getting images like this. This is already 2016-17 results, so they look pretty bad by now, but they were state of the art in 2016-17. And you know, I emphasize that this is not a real person. This is just a dream, as I say, or a generated image or a sample from this distribution. You can create a distribution by putting Gaussian IID here, and the push forward sort of operator here is creating a crazy distribution that's actually k-dimensional in this Rn ambient space, right? And there are many of those GANs, VAEs, core-based generators, and many others that I will be touching a little bit about the details, but for now, just think of all of them as a function from Z to G of Z. So, and then in 2017 or 18, these kinds of generated results came out, and I was thinking, these are amazing. They pass the visual Turing test. We cannot tell if these are real people or generated images, right? And this has been my main question in my lab for a long time. Modern generative models produce amazing pictures, but what can we do with them? So one answer here is we can generate fake pictures and fake social media linked accounts, and people do that, but that's kind of silly, right? And my point is going from this idea, where you're just generating totally fictional images, to convincing you on this, that they are modular and differentiable priors that learn the statistics of your data, And then if you want to solve a problem like an MRI imaging problem or a seismic imaging problem or any type of inverse problem, actually, it's extremely valuable to have a pre-trained generator. So I will argue how you can solve all these problems, for example, and we'll start with in painting immediately. Colorization is, when you have a black and white picture and you want to complete the colors. So it's like in painting in the channels. And then I will talk about MRI, our very recent work on MRI. And actually people, you see the sparse PCA here, and I have deleted sparse. So you probably know what I'm doing. Like this has been done recently by other researchers where they replace sparsity by in a range of a generator as a structural assumption. So the storyline is I will explain how the CSGM framework works. And it's basically an unsupervised way to solve inverse problems using a pre-trained deep generative model. There is interesting theory. If you are familiar and if you have worked with restricted isometry properties and the compressed sensing theory, where you can get sample complexity bounds, there's a natural generalization of this theory that I will talk about. It's basically restricted isometry properties for sets for the range of a generator. And then there is some ongoing theory that is appearing for inverting deep generative models, because as I will say, actually solving the inverse problem requires solving a non-convex optimization problem. And surprisingly, there were results that said that for a random generative model, the gradient descent provably solves it if there is sufficient, I guess, overparameterization. But it's quite a reasonable amount of overparameterization, as I will explain. And the main real problem we had with this whole line of work was that we're actually limited by the expressive range of the generator in practice. So we could not really apply this for real faces or real images of MRI because it was too biased towards what it has been trained on. So the new work that is called intermediate layer optimization that I will talk about expands the range of the generator, and it actually is able to match real faces quite perfectly, as I will show you in a minute. And then we applied this to MRI. So I'll talk briefly about MRI applications and fairness applications to this. So we're going to this kind of the lay of the land here. All right. So immediately starting with the punchline. So I was giving a talk at Michigan, and this is Vijay, who was my host at Michigan. So I went to his website, I downloaded his photograph, and I deleted this huge chunk of pixels. And I'm going to show you how CSGM performs in this in-painting problem, which is a linear inverse problem where the matrix A you observe is a subset of the identity rows. And it's also performing super resolution here. So we're going from 225 pixels to 1024 for free. So when my students run CSGM, we get this result. Now, a few things to look about this. This is a great photograph. It's super high resolution, super crisp. It knows that people have two eyes and symmetric mouths and so on. So it's really good in that sense. But it's actually, it's not Vijay, right? If you know Vijay and I showed you this, you'd say, okay, I see the similarity, but it's not really the same person. And more importantly, perhaps you see this is a white guy, right? Whereas Vijay is not. So you can see here the problems with the CSGM framework, but also the power of the prior, that it is actually remarkably able to imagine all those missing pixels, but also it's imposing its own biases here. All right. And then with a more recent results, so if we do what's called intermediate layer optimization, if we do layers 1 and 2, we get this result. And if we go even deeper and we optimize layers 1 through 4, we get this result. I will explain what that means, but I'm just telling you the punchline immediately. So in this case, you can see that this picture indeed looks like Vijay, is pretty plausible. It has a few artifacts that you may notice if you look closely, but overall, it's I think one of the best situations for linear inverse problems today. So just to set up the math now, unless there are any questions on this, is this all good? Yeah, okay. And please do ask questions, much more fun. So compressed sensing or linear inverse problems, we have an unknown vector x star. These are the pixels of Vijay's image that we want to reconstruct. We don't get to look at it. We get to see a matrix times x, right? So this is called the measurement matrix or the forward operator in different scientific communities. These are called the measurements. And of course, this is like a linear regression problem. You could have plus noise if you want, but the biggest problem you have is that the dimension of your vector is bigger than the dimension of your measurements, right? So you have to solve a nil-post problem here. And the standard way that people dealt with this is that you assume x star has some structure. And the structural assumption that everybody was assuming is that it is sparse. And now we're saying that we're removing this assumption, and we're saying that X star is near or in the range of a pre-trained generator, like a GAN. And that's going to be our structural assumption. So that's why we say that generative models are the new sparsity. Okay. So this is all good. And you can write these linear inverse problems like this in general. And this would be the very general form of how you would solve them. You would try to search, find an image that explains the measurements, but also is natural, right? And R of X is the regularizer that prefers natural images. The classical theory says, well, natural images are sparse, and L1 is approximately L0, so let's just regularize with L1 and hope for the best. And then if it is not sparse in the normal basis, you can also convert into any other basis by a simple transformation. So lasso and DCT or wavelet domain is used quite a lot in many, many applications, including MRI in production today. So the new idea is that sparsity is good, but now we have data-driven priors like deep generative models. So we're going to replace X is k-sparse with X is in the range of a pre-trained generator. By the way, recently, Akshay and Shushret and Eric Price proved that this is a proper generalization. So this is an interesting mathematical fact. They constructed the generative model that has, I think, 2 layers, where only k-sparse vectors are generated by it. Okay, so if you assume that something is k-sparse, it's a special case of assuming it comes from a pre-trained generative model. So how do we solve inverse problems? Yes, sir. No, k-sparse in the sense of R0 has k non-zeros. Yeah. The L1 is the messy convex relaxation. Yes, very good. Yeah. So how do we solve inverse problems if we assume X is in the range of a generator? It's pretty straightforward. So let's start with this. So we take my picture. We have a pre-trained generator, okay? So I want to emphasize this is an expensive box. We're using here StyleGAN 2, which was trained by NVIDIA, and they spent a lot of money and a lot of time training this box. I'm not going to mess with the weights of the box, okay? The weights are nice. The only thing I'm going to do is I'm going to mess with the latent vector, and I'm going to say I would like the latent output to match my picture, right? How do I do that? I write down a loss. So the way you do anything in deep learning is you write some function down, you do gradient descent, right? So you start with a random Z, you're going to generate a random face. Now you say, let's update Z so that the generated face looks as much as possible to my face, right? And you do gradient descent because this is a differentiable function of Z, because you can backprop through G, right? So you do gradient descent and you get this guy. Now, this guy kind of looks like me, but not really, right? Maybe he's a little sad. He doesn't exist, okay? So he won't be offended or anything. But it's actually a very good high resolution image. It actually also tries to match the background. It doesn't fully match it, but it does a decent job. But it's not me, and that's the problem of the limited expressive power of StyleGAN 2. It's doing a good effort, but it's not perfectly there. But beyond that, by the way, we proposed this in 2017, and many other people proposed this independently of us because it's a pretty natural thing to do, of course. But beyond that, now let's see how we solve an inverse problem like this one in PAIT. We're not going to try to generate a person with a huge black square. We're going to say, I want a generated image after it has been measured to agree with my measurements, right? That's still a differentiable function as long as the forward operator is differentiable. It doesn't have to be linear, right? And in this case, we got this image. And again, it's good, but please notice that the mouth, for example, doesn't perfectly match because this image is the best dream this GAN could produce to sort of match these measurements, right? Is this making sense? All right. Yeah.
You say A has to be linear or doesn't it?
The forward operator can be any differentiable forward operator because the only thing this algorithm needs is to be able to do backprop through G and through A and through the L2 norm. So any forward operator that's differentiable works. Yes. So is this all good? All right. And this is all background. That's why I'm going fast. This is our 2017 CSGM paper. So if you have blaring, again, you can write blaring as a matrix, which is convolving with a Gaussian kernel, for example, and it's actually exactly the same algorithm, but A now is no longer the impending matrix, it's a blaring matrix. And we get this image. These are 2017 results, that's why they look low resolution here. So this is the CSGM framework in general, and A can be any differentiable corruption process or forward operator. We do gradient descent in the latent space to satisfy the measurements, and we obtain useful gradients through backpropagation. And the other thing is we are leveraging the power of a pre-trained generator that produces awesome pictures, but we're not just generating random pictures, we're tuning it to match our pictures, right? That's the main point. So there are many other ways of solving inverse problems. If you care about them, I can talk offline, but this is a very specific style of algorithms. Now, what happened now in 2017 was we got this plot, and this plot was saying the generative methods are here. What I have here is number of measurements, and this is the quality of the reconstruction, the true quality of reconstruction, right? Because I have the ground truth. And you can see that, we get this quality whereas sparsity-based methods need 10x, like 1,000 measurements. So that was kind of a punchline is you actually can beat sparsity-based priors by a factor of 10x if you use generative models. But after this point, it kind of flattens out and sparsity methods actually beat you. And I have a question for you. Why is this happening? Why is this flat over here?
They're increasing the capacity of
the generator. Exactly. Fantastic. So after this point, your problem is not that you don't have more observations. Your problem is that you have reached the representation capability of your generator. So as we say in Texas, you need to throw away your gun here and buy a bigger one, right? So at this point, you have basically reached the best you can do. And you want to train another generator, but it's very expensive to train another generator, right? So at this point, we have to find an adaptive way of growing the capacity of the generator without training 1 million generators. You could do that, but that's too painful. All right, so theory, I suppose this crowd cares about that a lot, so I should focus more, but this is the previous theory results. So you observe linear measurements. Assume you could solve this. All right, first observation, this is a non-convex crazy style gun, right? This is a matrix for now. So now the theory only applies for linear, okay? So this is an NP-hard problem. So it's a non-convex problem, and we actually proved with Chi in a paper that for 3 or more layers, this is NP-hard to solve exactly. But if you could solve it, if your measurement matrix A has random Gaussian measurements, and the number of measurements is kd log n, where k is the latent dimension, d is the depth of the generator, and n is the ambient dimension, then the reconstruction you get by solving this is going to be very close to the best possible reconstruction your generator could produce. And then there is a plus, an additive term here, actually, because if you have noise, right? So if you have additive noise here, you get this. This is optimal scaling you could hope to get. So the reconstruction accuracy relates to your quality of your generator. And more generally, the number of samples you need is k log L. Well, L is the Lipschitz constant of the generator. So I don't know if people want to ask me questions about this. This is kind of the same style of result as compressed sensing, and it is the kind of thing you could hope for, right? It's actually provably optimal within a constant factor. The number of the dimension and L is the Lipschitz constant. You can easily prove that the Lipschitz constant is always like maximum weight to the depth, so you kind of go to this type of a result easily from here, right? No, these types of A's do not correspond to this. We can prove random independent. This is like the classical compressed sensing case. For in painting, you would have to do another analysis, but it would depend also on your generator. It's not, you need incoherence between your generator range and in painting. Yeah, very good. All right, so moving on, the proof of this is an RIP property, a restricted isometry property for the measurement matrix. So classically, it says all sparse vectors are far from the null space of the measurement matrix. That's what you need to have RIP, right? And here, it works out that the set restricted eigenvalue condition that we need for RA is that the differences of pairs of generated images, the differences of natural images, are far from the null space. This is the key technical condition you need. It's very natural if you worked in this space. Ludwig actually had this sparsity, which has structure, which I think is closely related and was one of our inspirations for this. So random matrices so this is kind of the main key lemma here, that if you have k log L rows, you will satisfy Shrek with high probability. And this is one of the technical lemmas. Now, how it's proven is interesting because we're trying to generalize it in the other generators that have full dimensional support. The key idea is you want to make a good coverage of this k-dimensional manifold in Rn, which is what the generator is creating. So what you're actually saying is I'm going to make an epsilon net in RK, and every one of my points is transferred by A to, so it's transferred by G of Z to the ambient dimension. But the distances here can be distorted by Lipschitz constant in the worst case. So that's how I know how dense I need to make it so that it is good enough in the ambient dimension, and I need to union bound over all these points here, which is where I get the mk log L. If you know, so the m equals k log L. It's a union bound over this epsilon. So it's pretty standard technology. So this is the metric entropy or the log covering number of the generator manifold, so to speak. And this will be useful to generalize. Now, optimization. If you care about theory for optimization, you realize quickly that this problem that I said you should solve is actually NP-hard. And the story for this was, you have a question? Or? Oh, yeah.
You're saying that the restricted eigenvalue condition for Gaussian matrices was not proven for?
No, it was proven. It was proven, but not for the range is not sparse. I'm not trying to recover a sparse vector. I'm trying to recover a vector that's in the range of a generator, which is a neural network.
Okay, so it's just, you proved it for like a manifold?
Yeah, so
of a certain dimension?
yeah, so we proved it for a manifold. It's actually technically not exactly a manifold because it's the transformation is piecewise differentiable only, but it's kind of a manifold. And yes, we proved it for the set, the range of a generator and the number of samples we need. So these are the two results here. Sorry, is this many. So K is the latent dimension of the generator, D is the depth of the generator, and N is the ambient dimension where the generator is going from K to N.
Okay.
Yeah.
And how, you say if A is normal, random normal, would a result closer to what's reality be if A is like subsampled Fourier?
So nobody has proved sample complexity bounds for generative priors for Fourier, as far as I know, but I think that, I don't know, maybe Agil knows this better. Like, is there any Fourier results?
Not that I know of.
Yeah, it's a natural and good open problem. If you can, so I think you can also, basically all the compressed sensing ensembles, you can see when they generalize for generative priors. This is a very natural strategy of questions that you can study. Yes.
I thought you said before that like there is this recent result that you can model sparsity like this also.
Yeah.
If you match with this result, then you get the classic sparsity result.
Not, yeah, I don't know the details of exactly how they construct the generator. I don't think they match
So
this.
they're not optimized in this sense.
Yeah, it's not optimized at all in a sense. But so, and also you cannot use it to do sparse recovery because you could also use their construction in theory to reconstruct sparse vectors using the CSGM technique, but it sucks.
Exactly. Okay.
Yeah.
Okay, so you're basically looking at vectors GZ1 minus GZ2.
That's right.
And then covering them with an epsilon net, and then showing that with enough random Gaussian measurements.
Yeah.
That's the result.
Yeah, it's like you do like a JL type of a bound for, but then you union bound over the size of the epsilon. So it's a standard technology.
Right.
Yeah. Yes. What?
What is K?
K. K is the input dimension of the generator. So the generators always are neural networks that go from K to N. So it's a function. This is G of Z. Z is in RK. Sorry, Z is in RK and G of Z is in Rn. All right. So this is the standard terminology. Great. So yeah, so we did this. And okay, optimization now. So this is, as I said, how the heck are we going to solve it? I mean, in practice, it works. That's the most important thing that we discovered empirically. Now, so Pohan and Blank-Voronitsky in this really interesting paper called 2018 proved the following statement. If the generator has random independent Gaussian weights, okay, so fully random generator, and every layer of the generator expands. So I hate the word expands because the matters of expanders, and I love expanders as a coding theorist. This is not expanders. It's literally, sometimes we call it expansivity or something. It's like if the first layer is K, I need the second layer to be K times log K. And then I need the next layer to be K times log K squared, all right? So you need every layer here to grow by a log K factor, all right? And they said, if your generator has this expansivity of log k and has random weights, remarkably, this non-convex optimization problem with a random instance of it will have only two minima, one at the correct point and one at a very special point that they can kind of exclude. So a variation of gradient descent that only needs to avoid the bad local minimum probably solves this problem, which I found quite a remarkable technical achievement, actually. So after that, so this was this called, is the result making sense? Don't ask me about the proof. I still don't understand. I kind of hopefully do a little bit, but not really. But the result is straightforward, right? What they claim. Make sense? All right. Then, we said this is all good, but if the weights are random and every layer is expanding, you can actually try to invert one layer at a time. So you're observing this, you can reconstruct this, then you're going to construct this, then you're going to reconstruct this. And it's not hard to actually show that if this matrix is expanding, even with ReLUs, in the noiseless case, you're getting noisy, you're getting half of your things are linear equations you can solve, right? So if your expansion factor is 2 or more, you get enough linear equations to solve one layer at a time, and you can handle noise too. So this is what this paper we had said. So we said you don't really need the log k, but we didn't have gradient descent. And then this paper by Daskalakis, Dhruv, and Zabetakis very recently said, oh, I can actually get the Paul Hunt gradient descent result for random weights, but I don't need log k expansion every layer. I need constant expansion every layer. All right. So they basically strengthened, as far as I understand, the matrix concentration that this paper is using. So all this is great, but it's still open to do it for real generators, because real generators almost always have a contracting layer. So near the end, there's a layer that's usually like 64 by 64, but it has 512 channels. So the total number of parameters before you go to the pixels is actually a contraction. So none of these results actually apply. It is open how to prove statements about the optimization when one of your generative model layers has a contraction in it.
I thought in the Daskalakis et al. Paper they have the lower bound.
I don't know. That I don't know, actually, if they have a lower bound. So they say it's impossible for random.
That you needed constant expansion, but you could maybe get rid of the some of the randomness. Or...
I think you certainly need constant. You need some constant expansion for sure, but I don't know if there is a caveat for one layer contracting. So good point. Good point. Maybe we need more assumptions. Is basically what you say. Yeah. Good. So that's the state of affairs as far as I know for the optimization questions. And here is another result that Agil. Okay, I don't have the citation here. So this is a recent paper that studied the following question. So generators like GANs and VAEs have a bounded Lipschitz constant, and the range has a Hausdorff dimension at most k. So this is an interesting result that says if you have a function from Rk to Rn, it could be fully dimensional if it's like some sort of fractal function. But if it has a bounded Lipschitz constant, the range has a Hausdorff dimension at most k. So that's why we think of it as a manifold that has dimension k. All right. So the CSGM theory says the number of samples is basically k log L, which is all good. But some modern generators, you may have heard of invertible flows or score-based generators and so on, have k equals n. So their latent dimension, there is no latent dimension. They're actually fully dimensional. They're supported on the whole Rn. But they're very concentrated in some part of Rn, right? So how can we get a meaningful sample complexity bound for solving inverse problems when we have these fully dimensional generators? So that was another question. And our answer is we define this thing that we call approximate log covering number or approximate metric entropy, which is saying the following thing. Given a distribution, P, that's a distribution where your images are coming from, and some parameters, the approximate metric entropy is the smallest number of balls you need, not to cover all the probability, because you cannot cover all the probability, but to cover a 1 minus delta fraction of the mass. All right. So with this definition, so just to be clear, so for a distribution P and two parameters, the covering number is the smallest n such that there exists a set containing n balls of radius sigma in L2. These are L2 balls, so that you get 1 minus delta fraction of the mass. So you're covering a decent fraction of the support of the distribution, so to speak, of the mass. And the theorem says that if you are actually sampling from the posterior distribution, if you could sample from the posterior, then you would get an error that is a constant factor from the optimal error you could get, which is the noise. So this is saying that the correct metric for all inverse problems, if you can sample from the posterior, is to sample from the posterior, even if it's fully dimensional. And this is actually controlling the number of samples you need, the log covering number of the distribution. And there's also a lower bound that basically scales the same way. So the number of measurements is some constant times the log covering number, which we call the approximate metric entropy. I haven't seen this exact quantity defined anywhere, so that's why we call it approximate metric entropy, but it's a natural kind of term in this space. If anybody knows of other people defining these types of measures, let me know. You probably need to cite some. But so is this all good? Then I want to move into the new algorithmic innovation, which is intermediate layer optimization. So we're going to optimize intermediate layers to expand the range of our generator and finally get my face denoised and inpainted correctly. And I have 10 minutes. Okay, good. So I'm thinking of the generator like here, but now I'm going to take a knife and I'm going to cut it in the middle. All right. So I'm going to look at an intermediate layer and I'm going to call it H. Okay. So this is still StyleGAN 2. It still has a Z and a G of Z, but I'm cutting it in the middle and I'm looking at the intermediate vector. And here's what I'm going to do. I'm thinking of it as a nested generator like this. G2 of H is G2 of G1 of Z. Right? So the first thing to do when you want to invert an image or you want to denoise is you run the CSGM algorithm. You search in the latent space like before to match the measurements. But after you do it, you're going to take a knife and you're going to cut this out, throw it away, and you're going to optimize this vector directly, okay? Effectively leaving the range of the generator because not all vectors here can be realized by previous inputs. I'll show you in an example. So this is my image. And when I run CSGM, as you remember, we get this guy. Now I'm going to start from, this guy corresponds to a Z1 star, right? Z1 star produces this face. Now I'm going to pass Z1 star through G1 and I'm going to get an H. And I'm going to do gradient descent from here to here, starting crucially from this H that came from this guy. And I get this image. Now, this image looks like me. It's not me. I guarantee to you, this image is a generated image. I'll show, I think I have it big. Yeah, there it is. Do you see any artifacts? So it's actually pretty close to perfect. I mean, it doesn't match the background. It has a few artifacts here, but it's very, very good. So this is the intermediate layer optimization idea that says if you want to expand the range of your generator, just treat it as a nested generator and optimize intermediate layers. Now you could ask me, hey, what if I just threw away this thing and I optimized directly in this space? It fails. Okay, so how does it fail? It fails like this. You see? So it produces this Picasso type of things because the generator is too powerful. Like if you directly optimize in this, you have too much expressivity. You're able to go beyond the range, way far from the manifold of natural faces, and you're basically not getting useful results. If you want to do art and make an NFT, then which I have done, you can do that. But if you want to actually solve inverse problems, you should do this nest. I think that's what we find. Is this making sense? Yes.
How do you choose where to cut the network?
Yeah. So
will you look better if you cut it?
It's a hyperparameter thing. What we do is we do 10 steps or 10 to 100 steps of gradient descent here. Then we do 10 to 100 steps gradient descent here, and we go up to layer 4. So you remember with the VJ image I started with, we do 50 to 100 typically in each layer from layers 1 to 4. If you go too deep, you're getting too expressive and you're going to produce non-natural images. Yes, sir.
I mean, is this expressivity something you could solve it by like early stopping? Like in the deep image prior papers, they have the same issue that in principle is too expressive, but they've been regularized and it's fine.
We definitely do early stopping also. We do, in fact, the hyperparameters here is how many, like the number of iterations in each layer. So the way this is produced is you say something like 10, 10, 10, 10, 10, 10, 10, and you can go very deep. Or you can say 20, 20. So you just do CSGM and then 20 iterations in the next level. So the hyperparameter is how many iterations you do in each layer of the style gun. And yes, we definitely need early stop. Good one. Yes, sir.
I have a new generative model. Are there any heuristics I can use to figure out how deep I should go or how much to optimize each interval?
I would love it if there were some theoretical understanding or some. I mean, the short, sad answer is you try the way you do any hyperparameter optimization. But if we had some principled ways of doing this, it would be great. So there is tuning that you need to do here. Great. Is there another question? Oh, yes.
Is this related to are these like all like expanding?
Yes. So this is an actual architecture that's StyleGAN 2. So it's actually a very complicated architecture. So it's not fully expanding in every layer, if that's what you're asking.
Okay, so it's not related to the fact that like it's an expanding, like it doesn't have to have like.
So this current architecture does not have full expansivity in every layer, for sure. It's StyleGAN 2 is a very complicated architecture. But if we could design a new generator that had full expansivity, maybe it would work better for this. I mean, now it works pretty well, but it would be nice to have some more understanding of how the architecture relates to this. Right now, I'm just searching by hyperparameter tuning. Yes.
This is actually what you just answered, but it seems like what you did here, you just solved your Texas problem by getting a bigger generator, by
yes.
cutting an existing generator to make it bigger and then working around that. So if you could just go out and get a bigger generator, would you need to do all?
No, if you could get, so for every number of samples, there is an optimal expressivity of a generator. If you have very, very few samples, you need a small k. Because you have to make it's like how many assumptions you make, right? Yeah. So if you have a ton of observations, you need a very expressive generator, so it doesn't have a lot of bias. Yeah. So if I could pre-train many generators at different expressivity levels, I wouldn't need this. This is a way that we're getting many generators from a single generator. But yeah, it would be better if we were tuning them.
Okay, so if NVIDIA actually knew you were doing this, could they, or you could, I mean, you're as you said, you have many generators here.
Yes.
Generators, but they're not trained as such, right? They're trained as a single generator.
That's right.
Could you, I mean...
So we could use other sequence of generators. So we are...
No, but if you did that, do you think you still need to do, to regularize this generator?
Yeah, so right, the empirical results we get are significantly outperforming any other paper that uses any type of generator for inverse problems. So we are state of the art so maybe with bigger generators people could outperform us, but empirical performance among any generative techniques for inverse problems, we're state of the art here. So we don't know of any method of doing better, but yes, if NVIDIA trains some bigger family of generators, they could outperform us, I suppose. Yes. Any other questions on this? So what do you want to hear next? Do you want to hear fairness, or I guess I have like 5 minutes or something? So just results quickly. By the way, this is a real person. This is a real person. This is a real person. So this is Stefano Armoni, he's a professor at Stanford. We observe this, okay? If you saw this, you wouldn't know it's Stefano, okay? In fact, and also when you see this is like, I think 2% random pixels, okay? So from this is the result we get with ILO. This is the result that basically CSGM techniques get, and this is the real person, okay? And I would argue that this is, a good image, and this is a good image. But if you saw these two images and you know Stefano, you would recognize Stefano from this image, but you would not recognize Stefano from this image, right? So, and in fact, I couldn't believe that we were getting these results. I asked Jill and my students to make sure they don't have a bug in their code like 20 times, and our code is public, but basically performs shockingly well for these types of problems. You're able to reconstruct from 2% of pixels or 5% of pixels, you can recognize a person. So it's shockingly good. Of course, we have tuned it, but yeah, these are the results for in painting, denoising, and deblaring. So these are blurry images. These are previous state-of-the-art techniques. This is what we get. You can also see the bias here, right? And also this is Obama, blurred Obama, reconstructed Obama, which was previous state-of-the-art. And this is the super resolution ILO we get. This is the real ground truth. So I guess, yes, sir.
Was there apart from the visual?
Of course, we measure PSNR, and yeah, of course, we have the ground truth. So we make plots of performance, right? So So of course, yeah. So we make plots like this. So we put here PSNR, or there's also perceptual metrics that we use. SSIM is a perceptual metric. So there's many distances. We have ground truth, we have the reconstruction, we just measure it, and we plot it as a function of measurement. So of course. Now these results are for MRI. So I'll quickly tell you, I have 5? No, not really. 1 or 2, okay. So we applied this on MRI. The shocking thing I want to say is that we were able to train a generator on brains and still produce MRI results that are, here's the punchline for MRI here. So we trained the first generator for clinical MRI data. We used the Facebook Fast MRI dataset. We matched state of the art for in distribution reconstruction methods. And we significantly outperform it when the measurements change because we're subsampling more. We're trying to do faster MRI. Or when the anatomy change. You can train your GAN on brains, and then you try to reconstruct a knee. It works pretty well if you have your generator that's expressive enough. So we significantly outperform it. And then we have also done a preliminary radiology evaluation where we showed to 3 radiologists, and they evaluated in a blind way which reconstructions are better for clinical use. So overall, I think it's pretty promising. I'm out of time, so I don't want to get into fairness, but you remember the issue of fairness from, is it the data or is it the algorithm? If you want to know more, ask me a question, so I'll take time from my questions, but the main points. CSGM solves inverse problems very well, but it's limited by the expressive range of the generator. ILO expands the range by optimizing intermediate layers. We can get sample complexity bounds, assuming we could solve this. And sampling from the posterior in general, which is a little different than this, using Langevin is provably near optimal and needs the low covering number of samples. And also gives you provable fairness guarantees. So I'll talk about this only if you ask me, and I have more time in the questions. And interesting applications, we are working on applying it to MRI and to other imaging problems. So that's the end of my talk. Thank you very much.
Okay, thanks, Alex, for the really great talk. Let's take questions. I'll hand you the mic if you have a question.
So maybe you could say a few words about fairness.
Oh, who knew? Okay, so the story was that people basically use this technique to do a super resolution. They upload it, you upload this image, you get this image. Amazing, right? And then somebody used their system and they uploaded Obama, pixelated Obama, and they got this guy. And this guy is now known, if you Google white Obama, it's this known fiasco failure of generative techniques for solving super resolution. And the question is really this one. So I'll just get to the punchline here. Is it a training data set problem that the GAN has seen more white people, so it produces more white people because that's how it grew up with? Or is it an algorithm problem? And the answer we say is that it's both. Okay, so of course there is bias in the data set, but the algorithm, map inference, is amplifying bias. And the reason is as follows. So here's the simplest example that I think crystallizes this point. Here's a game. I flip a coin, and I tell you it's heads with probability 60%. Now I tell you guess to maximize the probability you win. You do math. What do you play? Do you play 60% heads? You always play heads, right? So if you want to maximize the probability you are correct, even if there's a slight bias in the data set, you are actually always going to go for the majority class. So your reconstruction algorithm is amplifying the bias in the training data. This was a huge controversy on Twitter and so on, if you follow this. And I think our answer is do not do map. Instead, sample from the posterior. So sample 60% head. So in general, sample P of X, condition on the measurements, do not, how do you get that? You do our algorithm, gradient descent in Z, but you have noise. It's Langevin dynamics, like noisy gradient descent as opposed to vanilla gradient descent. Actually samples from the posterior, if somebody could prove Langevin dynamics was mixing the polynomial time and all that stuff that we cannot prove. But basically Langevin dynamics is trying to sample from the posterior, whereas CSGM is trying to do map. You don't buy it, you don't buy it. It's kind of
because you're not going between nodes.
What's that?
I mean, the mixing between nodes is super slow, right? So I mean, you're stamping with. It seems that here your problem is not like getting the fuzz corrector on white Obama. It's you have two modes, a black Obama and a white Obama. And you want
Yeah.
I'm skeptical that the Langevin dynamics is going to effectively do that.
But I have empirical results. So yes, it could fail. It could fail. Yes, but it doesn't. It doesn't. So this is real measurements. All right. And we have a paper, right? We have a whole paper here that I didn't spoke about. But this is wide Obama. This is a sample from the posterior we get from Langevin dynamics, which is pretty good. And you see that this happens across the board. So the answer to your question is that could happen indeed, but gladly it doesn't happen in our case because we tried it. We cannot prove it. But it would be really interesting to analyze the Langevin flavor of what we're doing, perhaps let's say when the generator has random weights. So that's an open problem that we're working on. Oh, yes, sir.
Sorry, just to be clear, but like that would suggest that even if you ran Langevin dynamics on like the pixelated Obama, you would still get like white Obama some percentage at the time. Is that true? Or do you always get like, you know, real Obama?
That's an empirical question.
Yeah.
Yeah. So that depends on how you tune your generator, but we don't get. Yeah, you could get something in theory. Now in practice, when we get samples, we could generate many samples of this, and I don't think anything looks exactly like this. Because if you think of the distribution, I think what's happening is the distribution has something like this. There's a very spiky point here. That's white Obama. But if you're actually sampling from the distribution, you're going to get samples here. You see what I'm saying? So the distribution can have very spiky points, but that's what we believe is happening. In practice, we're going to run our algorithms public, and you will not see white Obama as a sample. You will see variations, but it doesn't produce that picture. But it could be a hyperparameter tuning issue. Yeah, other questions?
So I guess we've had a lot of questions throughout the talk, so maybe we'll take the rest offline.
All right.
And let's reconvene actually at 11:10 to give ourselves a little bit more time, and let's thank Alex.
Thank you.